Thank you so much for the introduction. And so I'd like to have the acknowledgement first. Dr. Dolez, Dr. Westover, Mostafa. Um, uh, we had some sessions trying to find the commonalities between our talks, and then finally we found, okay, so the end user is important, and then the comfort of end user. So that's what is, I can elaborate with the commonalities between my work and Mostafa, and the interdisciplinary approach, of course, and then some modeling as well. So I'm going to share my screen. Okay. See my slide?
Yes.
Okay, perfect. So yes, just want to start with, so yeah, as I said, it's we're going to talk about comfort and then comfort of end users. So just have a brief description of comfort is the pleasant state of physiological, psychological, and physical interactions between human and environment, and then that's how we're gonna that's how we perceive that. Well, it depends on our perceptions. Will be comfortable or just we feel discomfort. Breaking, because my area of expertise is more on physiological comfort and thermophysiological comfort, which is the physiological is categorized with sensorial body movement and thermophysiological, and then of course they are all interrelated. They're all related. I'm just going to start with some definition and then some examples to give you an overview of what these kind of projects are, and then I will share some results, some of my recent work's results with you. Yeah, so I'm going to start with thermal protective clothing. So this is an example, and then I will break each parts individually and then put them all back together. So this is Sally mannequin wearing a, sorry, this is yeah, Sally mannequin wearing an FR clothing. And this is exposed to flash fire for 84 kilowatts per meter square for 3 seconds. And then, so based on that, 110 sensors, lots of like some models, and we will be able to predict burn injury, second-degree burn, third-degree burn, and the depth of burn. So why this example? I just want to break individual parts, say that. So this test consists of human closed system, the air gap. There is an intermediate thermal environment between the main hazard and the clothing, and then all these boundary conditions, which we are looking at interactions of all these environments. Yes, so so as I said, the heat source intermediate environment, and then that's what we're looking at when we look at the textiles for boundary conditions for clothing. Then thermal protective clothing, which consists of thermal liner, moisture bearing, outer shell in most of the case, and then that can cause barrier to heat and moisture, hazardous thermal environment. Is the microclimate between the fabric and human, which is when we say clothing, it includes fabric and the air gap. And then based on the design and the fit of garments, the individual will have different experience of thermal environment. So this is the direction from environment to human, but we are not mannequin. We are live human being, and then we do have some physiological interactions with the environment. So how about the other way? So how about from human to environment? So how about from firefighters itself. So well, how does it react? So I'm trying to again show these environments and then see that okay, so we produce heat and moisture, and we have to dissipate the heat and moisture to the environment. It will be and then it needs to be evaporated or dissipated to the environment. So when the clothing is means that the number of molecules receive and will be dissipated to the environment will be the same. So that's something ideal. That's what we want to have in terms of um, survival, not to have physiological burden. But what happens if it has transport property? So the moisture will be absorbed by clothing, and then it will be heat and moisture. It will be accumulated within the garment environment, and then it will increase the skin temperature, core body temperature, and whole lots of physiological burden that you may have even experienced during, like in your life with there are also some other aspects, some other problem with the accumulated heat and moisture, which is sensorial. So, like for example, the moisture in the armpits that can cause bacteria, moisture sensation, like tactile sensation due to like stickiness or roughness, like tickling, or when the clothing is wet, it's absolutely uncomfortable. When you're dealing with some sort of mm, protective clothing, you're wearing some high performance fabric, and then they are normally like Kevlar and Nomex, so it restricts it. It has stiffness, and then they're typically heavy. Also, our articulated body wants to have its own movement, but once these heavy clothing and then all these like stiff material or heavy weighted due to moisture can restrict our movements, specifically in some sorts of critical occupations such as firefighters. And yeah, and then all of these interactions. So as I'm telling you, that was an example to bring all of us in on just on the page. Interactions from environment to human, and then human to environment, and then all of these will be perceived. So we have sensory perception, and then what we receive will be compared with past experiences, desired beliefs, and then we can feel that okay, are we comfortable or we are not. Um, um, this like the individuals could be end users, could be researchers, or could be um, um, industrial workers. In case of what Mostafa is going to talk, is going to be like probably like surgeons and like patients and these sort of things. So this is what the role has this kind of figure, but it's in his own area. So yeah, so that's what I said, that putting all these pieces together, having people from like different area, who knows like thermal energy, who knows textiles, polymer, human physiology, neuroscientists, psychologists, and then so we need all these, or many more. We need all those people brain to finalize, and then to have um, um, for the end users to feel comfort. So yes, so I will have some slides later on showing some of my work, which is related to this topic. But something I want to add is that is the contradiction of comfort and protection. So what we want to have, we want to protect ourselves in different disciplines like radiation, electrical, sportswear, um, visibility protection, invisibility, mechanical, all these areas. We need to add uh, layers, or we need that high performance and or different procedure, different sets like finishing, and all of these will, because we're adding layers, we're making the clothing heavy, we add restrictions to movement. We need to do, we need to have proper tools to evaluate clothing, and then having some suggestions for the people who are working in this area, such as like polymer scientists or textile engineers, and the people who are working on like smart garments, smart textiles, to kind of balance that heat and moisture transfer while adding protection. So that is a challenge over the last decades. And then I have some just some examples, some results to show for frontline workers, protective clothing and face masks. That's what we did during pandemic. Well, it's I think that's wearing. I have some friends who were working in like were frontline workers and during pandemic, and they were have like I'm sure that you've all experienced that thermophysiological discomfort with face masks, and then or claustrophobia, or like yeah, so all sorts of this strains that we experienced over the last 2 years that we had to wear face masks. Yeah, and then the main part, which is sportswear, because I'm working with Lululemon for to improve their like physiological properties of textiles and sportswear for them. And then in the end, I would like to add some simulations, which is also something which is common with me and Mostafa. So just going through these results very just quick, fast, and then if you guys have any questions, so we can chat after. I just want to time for Mostafa because he's done a great job in this area. Yeah, so are surgical ensembles comfortable or getting ready for the next pandemic? Or yeah, so something which is very important is that like there should be some ensembles, like very smart ensembles with ventilation or with some fan, but this is not in general, like because I was involved in making while I was working with my research team at the Parent Innovation Center in Calgary. I saw that great number of the surgical gown that they made, and like thousands and thousands. And then I was testing those actually. So I was very curious to see are those, I know that there's some cutting edge surgical gown, but it's not for everyone, and it's not something that spreads everywhere. So yeah, I ran some tests on some ensemble, and so I had a nude mannequin. So I had the base ensemble. So the one in the middle is base ensemble, is just typical things that is worn by frontline workers. And then I had seven different surgical gowns. So most of them were produced in the plants that I was also involved with. And then I was curious to see, okay, so how do they act? Like, how are they? Comparing the thermal resistance. So thermal resistance. So the mannequin is measuring two things: the resistance of the to heat and moisture transfer in two separate procedure. 41 to 75% more than base ensemble, more than regular like typical left bottom picture. And for yeah, almost 42, more than 100% of increase in evaporative and moisture transfer. So increase it as evaporative resistance significantly. Yeah, so how can we improve that? Because there's some parts. So this, you can see like the back side. So these are the higher numbers means the higher resistance to evaporation. So you see like the back side when there are overlap of fabric due to design, or that's thick, uh, poorly breathable material is used for protect. Yeah, biomimetic, some in terms of methods, um, some good actually practical method to see more dynamic temperature or sweat rate responses of people, because on the current mannequin we're not able to change the sweat rate or temperature, or to have body mapping. Different part of body have different temperature. And to see, yes, so this lady mannequins are bought like months ago by Thermometrics. So to have lady mannequin to do to like generic, also like child mannequin, and then moving mannequin. So these, and then this respiratory system is very good to measure the effect of respiration on the microclimate, specifically for face mask. Yeah, so the next one was face mask. So enhanced protection face masks do not adversely impact their physiological comfort. I conducted some tests, and then I had face masks with like 2-layer face masks, 3-layer face masks, 4-layer face masks, and I was trying to use some N95 filter in between most of them. So I add a layer of N95 in between 2-layer face masks, and then try to see its effect on moisture and heat transfer. I also check small, medium, large, different size, and then different fit. Not much of a difference in terms of thermal resistance, but in terms of evaporative resistance, some of them which had durable water repellent finish and antimicrobial finish, because it's good to have a water repellent finish, because when the face mask is wet, it can transmit pathogens or microbes of black bacteria faster to the other side, to the skin side. So, but yeah, it will add, as I said, when you add protection, you need to sacrifice comfort for that. But in total, not there are some differences, but yeah, as I said, for example, D1, D2, D3, D4, when they were added with N95 filter, there was no significant difference in terms of heat and moisture transfer. Not as much as surgical gown, as I could say, but something was very was the amount of air gap. So as much as we lowered the air gap, there was the moisture and heat transfer were improved. And then the other way was there were some other methods like rubber band method, which was proposed to avoid like sinking from those open area underneath and top of so to increase that actually protection. And it also, interestingly, increased the thermophysiological comfort as well, because it's minimizing the air gap. Yeah, the other projects are, which I just have just one example or two because I want to save time for Mostafa, is improving comfort in sportswear, looking at fit, like regular fit or tight fit. And then yeah, there were improvements once the air gap is the air gap has gone. There are some improvement in heat and moisture transfer. but there are some other aspects, like for example, wearing loose garment, you will have less, like in our recent research, you have less the feel of wetness. So yeah, there's some pros and cons to each of these. So yeah, evaporative resistance also, when it's tighter, um, so there will be less, there will be more moisture absorption by heat absorption. It will be dissipated to the environment, rather than when it's air gap be more accumulated, and then yeah, it can cause restriction to heat and moisture. The next, or the last part is, we did some numerical analysis on some of our recent work on this. So I think yes. So the sweating cylinder is a simulating torso. So instead of so the advantage is that instead of making the garment, you can just evaluate fabric. It has different like ways of evaluation. It is measuring the surface temperature of the skin. It shows that I'm sure you've experienced that when you're exercising, when you're sweating, when you touch your skin, you feel cold. So that's how sweat evaporation help for body cooling. So that is how it's going to actually show the temperature drop due to cooling, post-cooling, or initial cooling. And it also, because the cylinder is on the scale, and then it can also tell you how much water is in the garment. So is the water dripping, is not absorbed by clothing, or is it like how much is evaporated and how much is stored within the garment? So yeah, that's what so one of the students at U of C with sweating cylinders, the environment as you see in the picture. And yes, so we found some good relationship between like it actually the model somehow like the behavior, the system behavior in single sectors. So, and then with that, um, we would be able to differentiate between the fabric and then like its response, and then we could do some parametric studies. So in terms of parametric studies, for example, we know that from experiments that air permeability is very important. Fabric porosity means the amount of fiber ratio to air ratio in the garment is very important. But so that's the advantage of simulation. We have to make fabric with different porosity tested, and then see the results. But with this parametric says, so that's one obvious advantage of modeling, is that we change the porosity and see how the fabric can hold, how it improve thermal some environmental factors, or sweat rate, some physiological factors. And that's my last slide. So in the end, what we want to do is we want to improve end users' experience, perception of comfort. We want everyone to feel comfortable in different discipline, and then we use different methods for that. So simulation is one for sure, and then we do some human trial, field tests, and then yeah, in the end, we want to have everyone's happy regarding their comfort. So I'm going to pass to Mostafa. I'm sure he will also, like, his speech will also support and then yeah, psychological interactions for human comfort. So thank you so much for listening to me, and then I would be answering. Mostafa?
Thank you, Farzan. So I just need to share my screen. So thank you, Farzan, for this interesting and insightful presentation. I like your applications, they're very cool. And thank you all for joining for this talk. I'll be focusing on the second aspect of this presentation, on the second application, which is on transfemoral prosthesis. So before I go on and highlight the commonalities between my work, as he mentioned, has two main areas of commonalities. The first one is that we are ultimately, and both in our projects and our work, and ultimately trying to serve this purpose of maximizing and improving the comfort of our end users. And the second one is that we utilize the same approaches and methodologies in order to address this problem. But before then, before delving into this, I'd have to give a little bit of an introduction on osseointegration and what we mean by osseointegrated implants. And of course, give a little bit of information also on transfemoral prosthesis. So the term osseointegration was introduced by P.R. Braemark in the 1960s, the direct structure and functional anchorage. And upon this discovery, the first application, or the first human application of osseointegration were in the field of dental implants in 1965. And then later the hearing aids and total hip replacement, which is also known as cementless hip arthroplasty, finger joint replacement, and of course, transfemoral prosthesis, which is the subject of this talk. So as you can see here on your right, this is an example of a typical osseointegrated prosthesis. Dual stump and the prosthesis. Alternatively, we use an osseointegrated prosthesis where the implant goes directly into the residual limb to the prosthesis through a transcutaneous adapter. This type of anchorage traditional because a lot of problems when it comes to precipitation and skin ulcers. It has also been associated with a frequent need of refitting. And in general, it has been there's a general lack of confidence and a degree of discomfort using this type of prosthesis compared to the results that we're getting using the which is the osseointegrated prosthesis. Despite the advancements of the transfemoral implant systems or the osseointegrated transfemoral implant systems, we have, or like the key issue with it is that we have to deal with implant stability or measuring type of protocols. We have the first surgical and rehab protocols called the OPERA system, which was introduced discovered osseointegration. We also have the OGAP1 and OGAP2 protocols, which were introduced in Australia by Dr. Monjid and Muraris. The main difference between those surgical and rehab protocols is in the type of implant system under the OPERA protocol is also called the OPERA system, and it relies on achieving primary stability or primary connection between it and the residual bone using a screw fixation during the surgery. The stem is tapped, and through this, these threads. The second OGAP2 protocol rely on a press fit type of insertion, in which case the stem is directly inserted into the stem and sufficient bone implant contact ratio is done through the surgery itself. Both type of implant systems rely on secondary stability, or what we call biological stability, that is done or achieved through the rehabilitation process. So the bone is naturally an adaptive tissue. So it reacts to the presence of the implant by and surface. And this happens during the healing stages and gives the secondary stability to the system. Both stabilities are important for the success of the surgery. My work undergoes into the Alberta Limb Osseointegration program, and we mainly use the OPL system, which undergoes into the OGAP. Like the main challenge when it comes to osseointegrated implants is actually measuring implant stability. If we lack the sufficient stability, it can lead to implant loosening and corrective surgeries, and I'll mention the significance of this later. But the definition of stability comes into the stable fixation between the implant and the bone. And one of the ways to assess stability is to actually and the implant at the interface. So this is done through a variety of ways. Histological methods are highly invasive and thus are primarily reserved for animal studies. We have also radiographic assessment. For most part, these are qualitative. Some of them are quantitative, such as radiostereometric X-ray assessments, but there are very high exposure risks when it comes to them, and we can't use them frequently. Alternatively, we have mechanical-based methods such as vibration-based methods. In this case, the implant is installed. The implant that is installed in the bone is excited, and through this excitation, we can actually determine the natural frequency of the system, which is directly related to the interface condition. The main limitation of the vibration-based methods is that the natural frequency is also dependent on other system parameters. So for example, let's say that we have another implant that is slightly taller, but has the same interface conditions. The readings or the frequency readings between both systems would be different. And thus the outcome, the outcome of this type of assessment is cannot be interpreted in an absolute sense. There are also some reverse torque methods where the implant is prescribed a certain torque, and it's like a go, no-go test, but this can subject the implant to dangerous loads. So in this work, we're focusing on vibration-based methods. And like I mentioned, the main limitation of vibration-based methods is that the frequency is also dependent on the system parameters, such as the geometry. And for this, we can overcome this limitation by using what we call a mathematical model to solve for the interface directly. So the ASSIST is a vibration-based method that utilizes a mathematical model to overcome the limitations that I've just mentioned. It's called the Advanced System for Implant Stability Testing. Here, when I'm referring to stability, it can be interchangeably, the term can be interchangeably used with interface stiffness, because stability is related to limited micromotion at the interface, and the stiffness governs this amount of motion. So from this point onward, using this term should be interchangeable with the other one. The ASSIST is also non-invasive, and it gives us a quantitative score, which is an O score. And this score, unlike frequency-based methods, is not influenced by the implant's geometry. So the question then becomes, how is this done? So the ASSIST has been used before for bone-anchored hearing aids, such as the ones shown here. It utilizes the fact that we can mathematically represent this system, such as this way, using a simplified representation. And by this mathematical representation, we can actually predict the model's response to excitation. So for example, if we excite the system and it starts moving, we can actually predict this response and compare it to what we collect in the clinic. And from this information, we can solve for the unknown interface stiffness, which is denoted as the K here. So this approach is much more direct compared to using traditional vibration methods, which utilize the frequency. And if you are familiar with the osteo system, that is the main limitation for the osteo system. So the significance of this work, like I said, ultimately, we want to find an absolute quantitative metric for assessing implant stability. So like I said at the beginning of this talk, we're ultimately hoping that we can improve the patient's well-being and comfort and the transition to their new lives with the prosthesis. So the first outcome or the first significance of this work is that it can be used for early failure detection, compared to X-rays, which can only start to detect the interface conditions after 40% reduction in the bone density, which is already too late. It can also help us because now we have a very quick and non-invasive way for assessing the interface, improve and understand our current surgical techniques and the surgical outcomes. It can also help the implant designers to understand how osseointegration works, because now we have a way of assessing it. So we can try different implant designs, and even before reaching the preclinical trial phase using animal studies, we can actually use this system to understand if the implant designs are working properly or not, and this will avoid us going through the preclinical trial phase, which can be troublesome for some patients. And it can also help us with reducing the rehabilitation, because under the current protocols, there is no patient-specific rehabilitation programs. It's done through some standardized timings, and this can increase the rehabilitation time greatly. So ultimately, like I said, all of these outcomes can help us improve the comfort and reduce the amount of stress that is exerted on the patient during the transition from the typical from the sucker prosthesis to an osseointegrated prosthesis. So as Farzan has mentioned, when it comes to perception of comfort, it's like a different aspects and different physical, physiological, and psychological aspects. In my case, it's a little bit different because we give the system a mechanical stimulus. In this case, the system is the bone implant system, and we do this test without having the prosthesis. So we just take this out of the equation and we test the system. And what we're trying to do, or the physiological process that we're trying to understand, is how the bone implant interface reacts to this mechanical stimulus. And this will show us whether there is healthy bone growth and remodeling occurring, and we can find a quantitative evaluation of the interface. And then this will help us to do, like I said, informed decisions during rehabilitations, improve surgical techniques. It can even be associated with osteoperception, which shows how the patient is comfortable or well connected with the external prosthesis. And all of this will ultimately serve with the purpose of the comfort, like maximizing the comfort. So my work has the following 4 main building blocks. Like I said, the first thing is that our ultimate aim is to find a non-invasive and quantitative evaluation of the stability of transfemoral implants. And this has 4 building blocks. The first one is the mathematical representation of the system, which is the main edge over traditional variation-based methods. Also, since we're dealing with mathematical representation, we make a lot of assumptions. So we have to validate this mathematical model through in vitro experimentation. And as you can see, the arrow is going both ways because the process is iterative. Like sometimes you find more information from the experiments and need to account for it back in the model. And it's like going back and forth thing. The same thing since we're doing experiments, we actually have to validate them and cross-validate them with clinical readings. My scope of work focusing on these 3 building blocks, but again, there is a parallel project here which comes with the system development. And in this case, by system development, I'm referring to the end customer system development, which is like the end user, which is in this case, the clinician, and the final system of collecting the data and analyzing it directly. So here I'm using like an R&D proto system, which I use to develop these models. But here, which is like an interdisciplinary project of different fields, where we have to design the final system that will be used in the clinic. So the current measurement process is that we attach an accelerometer to the protruding part of the system, like this, and I'm demonstrating it through a lab experiment. As you can see, this is made from composite bone. We have an interface, and we place an accelerometer. We are exciting the systems through a modified perio test, which is like a simple impact hammer, small impact hammer that gives a very small tap on the system. We record the acceleration of the system, which is the collected data. And then we compare this collected acceleration with the mathematical model's prediction. And from this, we can predict the condition of the interface or the stiffness of the interface in this case. So to do this, we have to do the following steps. Like I said, the keyword is to represent the system mathematically, and we do a simplified representation. For the clinical purposes, we used a 1D representation of the system. In order to cross-validate it, we use a more complex or 3D system, which in this case, we can use to model complex behavior. And this is an animation from it. So as you can see here, I've suppressed the implant and the bone implant interface for visualization purposes, but you can see here how the implant is reacting to the stimulus, which is the mechanical stimulus, and reacting, and how the bone implant interface is reacting to the mechanical stimulus. And finally, my work has to do with curating of some experiments and clinical readings to validate both models. So right now at this stage, we found that there's very high similarity between the 1D clinical code, which is efficient for clinical computations, and the 3D model for a wide range of interface conditions and implant length. We also have, we're doing some experiments, so there is good matching between the experiments and the models. And we also found that so far from the models that the detected response is highly sensitive to the interface condition. So our next steps involve further in vitro experimentation and clinical readings, and also doing parametric studies. So in this case, as you can see, there's a lot of commonality when it comes to the same approach of between my work and Farzan's work when it comes to experimentation and numerical analysis, and how this ultimately helps us answer the questions in our research. So in summary, my work involved measuring the stability of osseointegrated or transfemoral implants. My main focus is on mathematical modeling of the system, and this ultimately leads to the development of the measurement system. The implications for this is that we can have an easy way for failure detection. We can better understand the surgical outcomes, and we can understand osseointegration, and this helps us in designing more improved implant designs, and ultimately do more patient-specific rehabilitation programs. And this will ultimately lead to increasing and improving patients' comfort with the experience of moving to the implants. So this research has been supported by the following committee, and this is my supervisory committee. And these are the references for the talk. Thank you. That's sharing. And if you have any questions for me or for Zen, we're here.
Thank you very much, Mostafa and Farzan. I don't think that I can't even clap digitally. Not quite sure what happened, but I don't have those reactions on my screen. So great job, everyone, both of you. Really enjoyed your talks, and I'm glad that you left time for questions, because I have quite a few. But let's start and see if anyone in the audience has a question to start with. Eric, would you like to turn on your camera and ask a question?
Sure. Hey guys, great presentations. I like that you guys both tied them together with the idea of comfort. And I have a question specifically for Mostafa. Kind of like with regards to that concept. So I think you mentioned something about how kind of like measuring the level of stability of the implant could contribute to prosthesis embodiment. And I'm just wondering, like, if you've read anything in the literature or can like elaborate on that concept, like how knowing the stability and kind of like the health of the bone implant interface could like lead to a sense of embodiment with the prosthesis.
So thank you for your question, Eric. Most of the things that I've read have to do with, there are some research that have to do mostly with dental and bone anchored hearing aids when it comes to osseoperception, if I think you're referring to it properly. But when it comes to transfemoral implants, there are fewer sources. And what, like, the term itself, osseoperception, is a little bit tricky to understand, because like we're still trying to understand how it works. But there is a general sense that over time you feel more connected with the implant. You feel like you can actually some patients have attributed it to feeling like of vibration when you're walking. Like you feel like it's part of you. You have better control compared to the traditional ways of socket prosthesis. So there are fewer references, but it's still like it's still an unanswered question. Like it's.
Thank you very much, Eric, for that question. Michelle Gauthier has a question in the chat. This is for Farzan. Can you direct the wicking of moisture? So this may take moisture to an electrode interface, for example, where it can improve conductivity. So this is just to give you a little bit of framework for everyone. I'm sure you already know the framework, Farzan. But if we were to incorporate dry electrodes, so electrodes that don't require gels and and a messy substance. If we were to incorporate those in garments using your innovations, can you direct sweat to the electrodes, because that's actually a good conductive interface between the electrode and the skin? Is that possible?
Yeah, yes, sure. It's the matter of like how to embed the electrode in the fabric, and then because what we need to have is what we like. Ideally, we have moisture management fabrics, so we want the moisture to be absorbed quickly with the fabric. We want it to go through one-way transport, so we need one-way transport from inner surface to the outer surface, and we need that to be spread through the surface. So we have wicking in two directions. So like one-way transport, and then we want the wicking happen at the surface in the horizontal or like the other direction, so it can enhance drying. Yes, that's a thank you for the question. That's a great idea, and we would be evaluate that with the methods. I'm actually right now working on a wedding protocol using the sweating hot plate. So, and then that's what I am working on right now. And then we have ISMU, which is it's a advanced sweating cylinder, which we are trying to develop protocol for that. It's very cutting edge apparatus, and that's the our research cluster has, that's the only one in the world. And then so that has wicking sense. We have moisture sensor on it, and then we would be able to do that, yeah, to track it if it works. We also have at U of A PSERF, we also have moisture management apparatus, which put a drop and then see, because it also works based on electrical conductance, and it can see how this would improve wicking. Yeah.
Excellent. Thank you very much, Farzan. And maybe I can ask a question from Mostafa, but I'd like to point out what Dr. Jacqueline Hebert has put in the chat. She has included a link to an article on osteoperception that came out in Nature, just to kind of follow up on the question before. Mustafa, I was very impressed by your modeling and and what you've demonstrated in the effectiveness of the non-invasive vibration for assessing implant stability. The question that I had, and you probably have heard this multiple times, would exciting the implant actually increase the chances of micromotion and eventual loosening over time? Is that something that has been looked into, and what kind of steps would you take to ensure that the assessment device itself is not, or the assessment method itself is not causing actual eventual loosening?
Thank you for your question. This is a very important point. First of all, the magnitude of the tap that we do, it's minuscule compared to day-to-day activities using the prosthesis. So it's like the main advantage of the mathematical model, and that's one of the things, once you have a validated model, you can actually extract the stress fields and understand what's happening throughout your entire domain of the problem. So comparing to it to day-to-day activities is very small. In addition to this, I think you've noticed that we are inducing a transverse load. So more or less, the bending, we are generating bending modes in the system. We are not inducing torsional modes. So even though there have been some articles that discuss like how exciting, especially those who work with the osteo, can improve the sensitivity to interface conditions and reduce the dependency in the geometry using some torsional modes of vibration, we have avoided this approach ultimately. And since we're using transverse loads, we have bending behavior, which is closer to how like naturally the bone is adapted to. So we're not inducing any torsion, which can lead to loosening. But
yeah.
I think, yeah.
Yeah. Well, that's very good to hear. And in fact, probably your test may contribute to actually a benefit, which is increasing osteointegration into a porous implant because of that stimulation. So there are the benefits from that if it's done enough times. I see Raman has a question. Raman, do you want to turn on your camera and ask your question?
For sure. First, I want to thank Mostafa and Farzan for the super interesting presentation. So I have a couple minor questions. The first question was for, like, actually all of them are for Mostafa. So yeah. We know that these like circuit prostheses are like causing lots of issues, like mostly depression injuries, and like might not be are not the best choices for everyone. But I wanted to see what is the include, like whether the osseo-integrated prostheses are also like inclusive as the circuit prosthesis or not, or like what is the inclusion criteria for it? Could it be used for everyone? And yeah, like stuff like this. The second question that I had was regarding the fact that the whole concept of the mathematical model that you have was to develop a kind of baseline for the assessment, right? So like you didn't have the baseline for assessing what you wanted to assess. So like you came up with the mathematical model, and the mathematical model that you have is something general that we can be used like for everyone, or like you have to fine tune it for each subject. And I appreciate if you can like explain these points. Thanks.
Okay, thank you for your question, Roman. So for your first question, the inclusion criteria was much stricter at the very early years. Now with the more understanding of like how of osseointegration, and with the introduction of rehab protocols, it became less stringent. Like recently, I've read that Dr. Munjid included actually and used it for patients who had trauma due to diabetes, due to vascular disease. So with the better understanding of what's happening and what's going on, the inclusion criteria becomes less stringent. Also, there is another factor. It's like the training itself. Like the purpose of switching from there's no switch. Like the OPRA protocol is still being used, but with the OGAP protocol, it's closer to total hip arthroplasty in terms of the concept. So this was Dr. Munjid's aim, and made it more clinically accessible to the upcoming surgeons. So it's becoming more acceptable in terms and so on. And also, I forgot to mention that it became FDA approved. So up until recently, the transfemoral prosthesis, the Osseointegrated one, was not like there were many restrictions to it, and now the criteria like increased a lot, and FDA approval, which means that we will be seeing more surgeries in the upcoming phases. Regarding your second question, is that the mathematical model ultimately aims at, like, the only changes that you need to change it is that if the patient changes the type of implant. So we have for the OPL system, we have three main implant systems: type A, type B, and type C. They have slight geometric modifications. They have different effective length and different diameters. This is what you need to fine tune, but these are inserted as system parameters in your model. And it can be easy to select like the type of implant and then recompute it, but you have to account for the model's geometry. What we're trying to do is using the simplified representation of the interface. Hopefully we don't have to change the boundary conditions of the problem, but we need to change the implant geometry and adapter geometry for each patient depending on what's installed into the patient, but it shouldn't be that troublesome using the mathematical model.
Thank you, Mostafa. I know we're right at time, but I do want to ask Farzan a question. I'm very impressed by all the testing that you've been doing, and as you were describing your processes, and I wrote down, are your textiles providing comfort passively or actively? In other words, are these fabrics changing their character in an active fashion or in a passive fashion in reaction to, let's say, heat or moisture? And you mentioned that you're going to be embedding some sensors in them. can you maybe kind of elaborate on that a little bit? So starting off with what the textiles are doing, and are they changing their features actively or passively?
Thank you. Thank you for your question. Like so far, what I've done is more evaluation of the current, like whatever is in the market typically. And then, yes, of course, there's some like there are people in the sport like textile area that they're adding technologies to that. But in terms of my case, there are some surface finishing, some finishing on the material that would do that at a very basic level. So a very like simple way. But there are lots of area working on there, just embedding different fab, like for example, like phase change material, or embedding like some sorts of high performance like textiles within to that as can improve heat and moisture transfer. Yes, but typically what we're working right now is the finishing, which is trying to improve functionality.
Okay, wonderful. Thank you so much, Farzan and Mostafa. This was very exciting talks from both of you. And thank you for taking the time and effort into linking your talks in a meaningful fashion. And I still have a list of questions, but I'll follow up with you later. So thank you very much. And thanks everyone for attending Smart Talks this month. See you.
Thank you all. See you.